Hello, YouTube. This is Dr. Ron W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. As with most of my screencasts, I'll be discussing the reciprocal system, specifically the reciprocal system Microcosmos database. We've already covered the Macrocosmos database. And we've covered the first two layouts here in atomic distance and valence. So today we're going to go to specific heat. So we'll click this right now. And it'll take a couple moments to load. I should point out here that I recommend strongly that you use a Xeon-based computer for this particular database module. The Macrocosmos database you could buy with a Core i7 or i9 or AMD processor, but for this database, it's probably best to use a Xeon CPU. This laptop I'm using here is the Lenovo ThinkPad P72. Has the what is it, 1886, something like that, mobile chip. It has a turbo boost over to 4.8 gigahertz. So we'll just graciously pause here and just wait for it to come up. I think it's the E2186M. Now that I'm trying to remember the CPU here. Okay, there it is. So it's not too bad. There's just a tremendous amount of calculations in here. Incidentally, what I've done is make all of Dooley-Larson's theoretical physics work fully computational. So here we're looking at the specific heat screen. The top portion is the same as with the atomic distance layout and the valence layout, and that the element component of the mix is given here, in this case iron, inscription iron, of course. Form number is 1. The atomic or molecular weight is here, melting temperature is here, thermal factors here, and compressibility factors here. Again, you should carefully study Dooley-Larson's work, Basic Properties of Matter, to understand the thermal factors and the compressibility factors. If we were dealing with a compound, we could have up to 4 elements here, number of atoms of each element, and then the program would calculate the mass fraction, estimated volume, and so on. And here we have the femtometer cubed per cell. This section here is for paraffin hydrocarbons only, and that's kind of a special case. Same thing goes with the N multiplier here and max vibrations. This gives, just read the tooltip here, this gives the number of segments of the specific heat curve, so that's important. So that's in addition to the first segment. So here we have a total of 4. We start off with the initial thermal factors here, and you can see then it changes as we go down. Number of thermal groups, it's 1 in each case. So the thermal factors can change with temperature. That's important to understand. And this is the extrapolated specific heat. And this is, by the way, specific heat with respect to pressure rather than volume. These numbers here, it's calories per mole per Kelvin. And the endpoint temperature is down here. Now, to compare the theoretical calculations with empirical data, I use Carl Yaw's regression coefficients, A, B, and C. This is polynomial, and I'll show that to you in a moment. But once we know this, and we can integrate to get the enthalpy, and it's in calories per mole or calories per gram. So this shows the different stages here: 0 to T0, T0 to T1, T1 to T2, T2 to T3, T3 to T4. And let's say for 400 degrees Kelvin, and by the way, there can be a difference between the molecular specific heat and that of the aggregate. So it's not negligible. It's important to know that. So we have this in calories per mole per Kelvin, or calorie per gram per Kelvin, or joules per mole per Kelvin. And then here's the yaws calculations, Carl Yaws calculation, 26.7572. And that compares with our calculation, 25.0064. And here's the enthalpy at the temperature T. That's the input temperature here, and this is the entropy. Now suppose we have a heat sink and a heat source, in this case 0 Kelvin and 1000 Kelvin, and then we calculate these values here for the at 0K, of course it's going to be 0. And then we have this for at the heat source at 1000K. And then from that, we can calculate the enthalpy change. And going from 0K to 1000K, this is in calories per mole, calories per gram. That's for the molecular calculation, and then for the aggregate. So again, there's a little bit of a difference. It's important to keep that in mind. And then we also calculate the entropy change. Okay, well, I hope you understand that. It is a little complicated, but it makes all of Dewey's work for specific heat, for solids, totally computational, so you can clearly see this. And these are line segments, see? So in some cases, the thermal factors changed, and then they remained constant. You know, for complicated molecules, you can have more than one thermal group here. And I guess that pretty much covers it for today. All right, please study the reciprocal system and prove it for yourself. For the simplest possible treatment of the theory, please obtain my work, The Unmysterious Universe, still in print, still selling quite well. It's only 80 pages, has all the concepts, many diagrams. It really makes the theory easy to understand. But if you do want all the mathematics and all the detail, then please obtain my work, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file, 711 slides in the PowerPoint file. Thousands and thousands and thousands of equations, diagrams, tables, figures, everything. It'll take you months to go through it. And then once you're done, you should get these two database modules. This one I'm going to close now. I'm going to say, let's go back to the main menu. The Microcosmos database covers interatomic distance, valence, specific heat of solids, and also energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and atomic spectra, liquid, vapor, and gas matter properties, volume and density, specific heat, energy and entropy, viscosity and surface tension, electrical and thermal conductivity. Also covers cosmic elements and subatomic particles. Cosmic elements are identified conventionally as mesons. The program also covers the properties of material and cosmic subatomic particles, and of course it also covers photon properties, includes a great graphing program. Then there's the Reciprocal System Macrocosmos database, which I've already covered in numerous screencasts. It covers the properties of the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies like asteroids and comets, nebulae, gas and dust, and voids. It also contains a great graphing program. Okay, now not only was my theoretical physics mentor Dewey B. Larson a theoretical physicist, he was also a theoretical economist, and I've made his work in economics fully computational as well. That's in my Optimal Economist software package, which includes the microeconomics of individuals, businesses, and business sectors, and also the macroeconomics of whole regions and countries. Completely supersedes Keynesian economics. It's a very superior form of economic theory, applied economic theory. So we'll eventually get around to doing screencasts for that in the not too distant future, probably after we finish the Microcosmos database here. Okay, so again, please study the reciprocal system and prove it for yourself. Please like this video and please subscribe. We need to increase our subscription substantially. Okay, and we'll do our best to answer any comments or questions that you have. So again, thanks for your attention. And again, please, please, please study the reciprocal system and prove it for yourself.